Welcome back to Algebra. Today we're going to take a look at section 13.2. We're going to continue talking about trigonometry, which again is the study of angles. And what we're going to begin with is putting two ideas together. Putting together the idea of angles and the idea of an XY coordinate system. In other words, what we want to be able to do is take an XY coordinate system and we want to draw angles upon that XY coordinate system. And of course we could do this in all kinds of different ways. We could draw an angle using two lines here. We could create this angle. We could make an angle over here. You can put angles anywhere you want, anywhere on a picture. But to be consistent, to do it the same all the time, we're always going to do it in one specific way. And it's called, I've just got to shrink up my picture so you can see the terms there, guys. We call it standard position. All right, so we're always, whenever we're putting angles on an XY coordinate system, we're always going to create them in what's called standard position. Now what that means is that all of our angles are going to start being measured at the positive half of the x-axis. That's our starting point, or what's also called the initial side. All right, that's where we start. And then what we do is we use the origin as the rotation point. And then what we're going to do is we're going to swing out a second line to some point, doesn't matter where. All right, and we're going to measure that angle. Let's use one of our Greek letters for that. Let's call it theta. Okay, so the initial side is always on the positive half of the x-axis. We never vary it. It's always in that same spot. The initial side is the positive half of the x-axis. So I'll just sneak that in. So initial side, positive half of the x-axis. And then the other line that we swing out to create the angle is called the terminal side. And the terminal side can stop in all kinds of spots. Maybe instead of stopping there, maybe we swing it out a little bit further and it ends up stopping right there. That would be a different angle. Or maybe we swing it way the heck around. Maybe it gets swung out to there, and now we're going to be talking about that angle. The initial side is always the positive half of the x-axis, and then we can stop the terminal side wherever we need to or wherever we want to. All right, so the initial side, always the positive half of the x-axis, and then the terminal side gets swung out to some other point. Okay, so standard position means the initial side is on the positive half of the x-axis. That's called the initial side. The terminal side gets swung out from there. Okay, now I'm going to skip the fourth definition there. I'm going to go to the fifth one. Now we can have both positive and negative angles. Now angles are considered positive if we swing out the terminal side counterclockwise, right? In other words, if we start by going up, we consider that to be a positive angle. And a negative angle is when we swing the terminal side clockwise. So not only could we swing the terminal side up, but we could also swing it down in a clockwise direction. And when we swing it down, we consider that to be a negative direction. Right? So we'd have positive and negative. And then the definition that I skipped are coterminal angles. And what that means is we just have two angles where the terminal side ends up in the same spot. Now, the easiest way to see that is to just look at something like this, a positive and negative angle that end up in the same spot. So as an example, if I were to start an angle on the positive half of the x-axis, I'll do this one in red so it sticks out, and I stop it right there, but instead of calling it theta, let's call it something else like alpha. If we stop in the same position, in the same spot, we say that the yellow and the red would be coterminal angles. The yellow and the red would be coterminal angles because we stopped the terminal side in the same position, in the same spot. Okay, and what I'm going to ask you to do on some example problems is I'm going to ask you guys to find some coterminal angles And when we ask you to find coterminal angles, what we're going to ask you to do is add or subtract 360 degrees. I hope that makes sense. 360 degrees is a complete rotation, all the way around. So I hope it makes sense that if we go a complete rotation, we end up right back where we were. Okay? Alrighty. Now something that's really important to us, I'm going to start with a fresh picture here. Something real important for us is when we're putting angles onto a coordinate system in standard position, we need to understand that an XY coordinate system splits or breaks a picture into 4 areas called quadrants. Quad, the prefix means 4, and we usually abbreviate these with Q. And the way they're numbered, I hope you remember this so that it's not brand new, but the upper right area of a picture is called quadrant 1. The upper left is called quadrant 2. The lower left is called quadrant 3, and the lower right is called quadrant 4. So when we're starting our angles at the positive half of the x-axis, the initial side is the positive half of the x-axis, and we stop our angles somewhere, I want you to be able to tell me in what quadrant they're located. Does the angle, is the terminal side of the angle in quadrant 1, quadrant 2, quadrant 3, quadrant 4? And to help you with that, I need to ask you just a few questions, and you're going to need to put this into your notebook to help out. What if I were to swing around the terminal side until it was pointing straight up? All right, how many degrees would I have traveled, guys? Go from the positive half of the x-axis to the positive half of the y-axis. How many degrees would I have traveled? Well, that would be 90 degrees. Well, what if I would have kept it going until the terminal side would have been pointing straight to the left? How many degrees would I have traveled? Well, that would be 180. What if I kept going still further until it was pointing straight down? How many degrees would I have traveled? 270. And what if I were to have kept going until I got back to where I started? Not only was that my starting point, so 0 degrees, but if I go all the way around, I've made a complete rotation, so that would be 360 degrees. Okay? So now if I give you any angle, you should be able to tell me what quadrant it would be in. As an example, what if I gave you a 208 degree angle? Well, 208 is in between 180 and 270, so a 208 degree angle would be located in quadrant number 3. What if I were to give you a 306 degree angle? Well, 306 is between 270 and 360, it's in between, so therefore a 306 degree angle would be in quadrant 4 somewhere, and so on. Okay? So I need you to draw this picture so that when I give you an angle, you know what quadrant it's located in. Also, while we're at it, let's switch colors. What if instead of going counterclockwise, we went clockwise? We started on the positive half of the x-axis, but instead of going up counterclockwise, we went down. Well, what if I would have swung out a line from the positive half of the x-axis till it's pointing straight down? How many degrees have I traveled now? Not 90, because we're going in a clockwise direction. This would be negative 90. How about if I kept this going around until I'm pointing straight to the left? This would be negative, let me do that again so it looks a little better, negative 180 degrees. If I kept going until I'm pointing straight up, that would be negative 270 degrees. And if I get all the way back to where I started, that would be negative 360 degrees. So any of these locations where you see 2 angles, let me use my laser pointer. Here we've got 2 angles. Here I've got 2 angles. Up on the top I've got 2 angles. And over here I actually have 3 angles. Those are called, again, coterminal angles. We have 2 angles where the terminal side is in the same location. So again, I should be able to give you an angle like negative 110, and you should be able to tell me what quadrant it's in. Negative 110 would be between negative 90 and negative 180, so it's going to be down here in quadrant number 3. Okay, that sort of thing. All right, so that'll be a real important idea for us, is to be able to understand what quadrant an angle is lying in. All right, now so far what we've worked with is all of our angles in degrees. Well, what you've never seen before, and this is going to be brand new to everybody, there is another way in which we can measure angles. And I mentioned that the other day when we were talking about our calculators and having our calculators help us find trig values. But there's another way in which we can do it, and it's called measuring in radians. Okay? Now, degrees are based on a complete rotation going all the way around the picture once is 360 degrees. Well, there's another way to do that. If we think about a circle, let me draw you a quick circle. All right. And we think about going all the way around once, we could think of that as 360 degrees, absolutely. Or we could think about, what we also do is we think about a circle that has a radius of 1, and we ask you what would be the circumference of that circle. If you don't remember it, it's okay. The circumference of a circle is 2 times pi times r. So we'd consider the circumference of this circle then 2 times pi times 1, so 2 pi. In other words, what we're saying is the distance all the way around, it's called the circumference, is 2 pi. And so another way in which we can consider angles is to think about a complete rotation going all the way around a picture one complete time, not only being 360 degrees, but another option is to think about it as going around 2 pi. And when we think about it going around as 2 pi, we call that 2 pi radians. We'll call that 2 pi radians. So now, just as we did on the previous picture, hey guys, if 2 pi is all the way around, what would halfway around be? What would going halfway around then be? If all the way around is 2 pi, what's halfway around going to be? Well, halfway around would then be pi, right? If one complete rotation is 2 pi, half of that would be 1 pi. And how about now if we went from the positive half of the x-axis till we're pointing straight up? Now that's going to be halfway from 0 to pi, so we consider that pi over 2. And if we went 3/4 of the way around till we were pointing straight down, we would then consider that 3 pi over 2. All right, and it's a little bit harder to now give you guys an angle in radians and ask you which quadrant it's in. Is it in quadrant 1, quadrant 2, quadrant 3, quadrant 4? That's a little bit tougher. But over the next few years, we're going to continue to talk about radians. And trust me, you guys will get better and better and better with radians. Now, just to get you kind of the feel for radians, what we're going to do next is I'm going to ask you to convert back and forth between degrees and radians, back and forth, both directions. And anytime we convert back and forth, we use what's called a unit conversion. As an example, if we would have picked somebody out who was 6 feet tall, and we wanted to convert their height, so this is the height of somebody in class, and we wanted to convert their units from feet to inches, what we do is we multiply by a fraction whose numerator and denominator are equal. And the conversion we'd use is this one, 12 inches equals 1 foot. Everybody knows 12 inches equals 1 foot. But what that allows me to do is cancel the feet labels, top and bottom, and what I'm left is 6 times 12 inches. So whoever that person is that's 6 feet tall, I think we all have a pretty good feel that they're also 72 inches tall. Those two things are the same. And we can accomplish that anytime we multiply by a fraction whose value is 1. The top and the bottom of the fraction are equal. Okay? And so what we're going to do with our angle conversions is we're going to pick two angles that are equal. And what we traditionally do is pick this one. We traditionally pick, if you go back over to the picture, I'll box this in yellow. We usually pick pi equals 180 degrees. You can actually pick any of these. You could pick pi over 2 is equal to 90, 3 pi over 2 is equal to 270, 2 pi is equal to 360. You can actually pick any of those, but the simplest one is usually pi equals 180 degrees. And that then allows us to convert degrees to radians as an example. So if I asked you to convert 150 degrees to radians, what we do is we take 150 degrees and multiply by a fraction whose numerator and denominator are equal. And what I'm going to choose is this version, pi over 180 degrees. We just said that those two things are equal to each other. Pi, radians, and 180 degrees are equal. But what this allows me to do is cancel the degree labels, the little circles, top and bottom. And what we're left with is 150 pi over 180. And if we cancel a 30, if we cancel a 30 in the top and a 30 in the bottom, what we'd have left is 5 pi over 6. And we usually don't punch out the pi as a decimal. We usually don't use 3.14159265535 as a decimal. We usually just leave our answer in terms of pi's. Okay? So let's just try a couple more for practice. Negative 215 degrees. We're going to multiply by pi over 180 degrees so that the little circle notations cancel on the degrees. And what I'd have then is negative 215 pi over 180. And what can I cancel this time, guys? Just a 5, I think. Just a 5 top and bottom, right? So let me just punch that out. I don't want to screw that up. So 215 divided by 5 would be negative 43 pi. And 180 divided by 5 is 36. There we go. So negative 215 degrees would be negative 43 pi over 36. All right, try a couple more. How about 570 degrees? Again, convert that to radians. So what we'd have is 570 pi over 180. And if I'm doing that right in my head, let me double check on my calculator. I don't want to screw it up. What we could cancel top and bottom, I thought it was a 30, but maybe I'm wrong. Let me double check. Yep, it's a 30, so what I'd have is 19 pi over 6. All right, again, we usually leave the pi. We don't usually change that into a decimal. And then the last one, negative 90 degrees. To change that to radians, we multiply by pi over 180 degrees, so the little circle notations cancel, and I'd be left with then negative 90 pi over 180. That's a little easier on my brain. So that would be equivalent to negative pi over 2. Okay? And we can do the same thing in the other direction. Here are 4 examples of starting with degrees and ending with radians, but we can go the other way as well. We can go the other way. We can start with radians and go to degrees, and let me show you a couple of those. So if I start you off with pi over 3 and I want you to turn that into degrees, we just use the same fraction but upside down. So we turn it upside down, so it's 180 degrees over pi. And I hope you can see what happens. The pi's cancel top and bottom, so what I'm left with is 180 degrees divided by 3, which is 60 degrees. Okay, or 5 pi over 6. We start with 5 pi over 6 and multiply by 180 over pi. Again, I hope you can see that the pi's cancel top and bottom. So I'm left with 5 times 180 divided by 6. And when you use your calculator to punch that out, you get 150 degrees. And I'll try one more. Negative 3 pi over 2. Multiply again by 180 degrees over pi so that the pi's cancel. So you'd have negative 3 times 180 divided by 2, and that's going to get us negative 270 degrees. Okay? So that's going to be how we ask you to start working with radians, is just flipping back and forth, changing back and forth between the two measures. All right? All right, let's do a few calculator problems. I showed you in the previous lesson that we can do trig values, sines, cosines, tangents, and so on, using our calculators when the angles are in degrees. And we can do the same thing in radians. But as I showed you the other day, you'd need to then change your mode. So let's see, what I tried to do here was show you on one of my calculators that we would be able to change the mode from degrees to radians. And then we could input any of these trig value problems that I have off to the left into our calculators. And what I've shown you down below is what should come out, as an example, if you punch in the cosine of 3 pi over 7, you should get this crazy decimal. Whenever you have to write these answers, though, just give me a couple of decimal places. That's plenty. And then some of the other ones, if you just want to try for fun, the sine of pi over 6, you should get 0.5. Or, 1/2. The tangent of pi over 4, you should get exactly 1 right on the schnoz. Okay? So feel free to give those a try. There's a couple in your assignment as well. And then to finish off, we just have a couple of ideas that go along with angles and then a corresponding shape, circles. So 2 concepts here. One's called arc length and one is called sector area. Now, arc length means that we're going to be looking at a portion of a circle. Let me choose a brighter color here. Let me maybe choose red. So when we talk about arc length, what we're considering is the length of the curve in between 2 points on the curve. And I chose A and B. You guys can pick whatever you want. But we're considering the length of that. So it's kind of like we're assuming there's a length of rope laying on the floor in the shape of a circle, and we want to find out how long that rope is in between these 2 points. Now, ideally, what we could do is just grab the 2 ends of the rope and pull it tight and then measure it. But in geometric circumstances, we would need some formulas. So what I've got is the formulas for the arc length of a portion of a circle. And I've got one formula when the angle is measured in degrees. The arc length is the central angle divided by 360 times pi times the diameter, where the angle means that we're looking at the angle formed by the radii drawn to A and B. And then the diameter, of course, is the distance all the way across the circle that goes through the center. Okay? And then we have another version of that same formula when the angle is measured in radians. And that formula is a lot nicer. It's just r times theta. All right, and then the second measure we're going to look at is what's called sector area. And what we're looking at here is the area for a slice of pizza. So we'd be calculating the area formed by that slice of pizza. Again, we can do it in either degrees or radians, working with the angle at the center that I called theta and the radius of the circle. And again, you can tell there's 2 versions, one when the angle is in degrees and one version when it's in radians. So everybody, pause this video so you can make sure you get all 4 of those formulas written down into your notebooks. Okay? And then just a couple of examples and we'll finish this section off. If I were to give you this circle that has a radius of 8 centimeters and it has a central angle of 80 degrees, what I would ask you guys for is the arc length of that circle, so the distance from this point to this point on the circle. And then I would also ask you for the sector area enclosed by that slice of pizza. Okay, so the arc length, because the angle is measured in degrees, the version of the formula we should use then is 80 degrees divided by 360 times pi times the diameter. Well, since the radius is 8 centimeters, that means the diameter then would be 2 of those fellas, or 16. And so if I do the math for you, and I'll punch this out as a decimal, so 80 divided by 360 times pi times 16 gets us an arc length of about 11.2 centimeters. So the arc length in between those 2 points, if you were to just grab onto the 2 points and just pull it tight, it would be 11.2 centimeters long. And the area of that sector is going to be the angle divided by 360 times pi times the radius squared. So 80 divided by 360 times pi times 8 squared. And again, I'll give that to you guys as a decimal. Let's see, times pi, there we go, and then times 8 squared. And I got about 44.7 square centimeters. All right, so that area about 44.7 and the arc length about 11.2. And then last one, I just did one more example where these angles given in radians. And again, I'm just going to ask you two questions. What's the arc length and what's the area of the sector? The arc length, excuse me, the arc length then is going to be the radius, r, multiplied by the angle in radians, 2 pi over 3. And so the arc length, again, just continuing to give these to you in decimal form, would be approximately 16.8 inches. And the area would be 1/2 times the radius squared times the angle. All right, and so the area then, 1/2 times 8 squared times 2 pi divided by 3. And if I punched okay, I didn't, I hit the wrong button, darn it. There we go, is about 67 square inches. All right, so not a big deal on those last two shapes, the arc length and the area, but there they are. And now you should be all set to shut off the video and go ahead and get to work on section 13.2. Let me know, as always, let me know if you have any questions. I'll be happy to answer your questions using email or telephone. Okay? So talk to you soon. Hope you're having a good day. Bye.